Hello and welcome back again. We have seen that silicon detectors play an extremely important role in the tracking systems of modern particle physics experiments. And in this part of the lecture, I want to give a brief introduction into this important detector technology. Now, monocrystalline silicon is a semiconductor with a relatively small band gap energy of 1.12 electron volts between the valence band and the conduction band. An ionizing particle can excite electrons from the valence band to the conduction band, thereby creating so-called electron-hole pairs. The average energy deposit required to excite an electron-hole pair in silicon is 3.6 electron volts. So this is larger than the band gap energy, and this is because only part of the energy deposit goes into the creation of electron-hole pairs, whereas part of it goes into the excitation of phonons in the silicon lattice. The energy loss of an ionizing particle in our detector material is of course a statistical process, and for thin layers of material this is described by the famous Landau distribution that you see depicted here on the right. For a minimum ionizing particle, or MIP, in silicon, the mean energy loss is 3.9 MeV per centimeter, and this translates into 32,500 electron hole pairs created in 300 micrometer of silicon. And this is the typical thickness of a silicon detector that we would use in a tracking system. But the Landau distribution is actually asymmetric with these tails towards large energy deposits, and what is more important in practical terms than the mean of this distribution is actually its most probable value. And this for a MIP translates into 22,500 electron hole pairs in 300 micrometer of silicon. So now these are small signals, and one of the challenges in designing a silicon tracking detector is to design fast and low noise front-end electronics that are able to detect these small signals with high efficiency. We can of course increase the signal here by increasing the thickness of our detector, but this case comes of course at the cost of increasing the material in our detector, and we have seen how increasing the material will deteriorate our measurement resolution due to the multiple scattering and the energy loss of the particles that we want to measure. Now, in order to collect the electrons and holes that the ionizing particle has created in our detector volume, we have to generate an electric field across our detector volume. And this we can achieve by creating a reverse bias p-n junction across the detector volume. For example, by having these p-doped implants at the surface here of an n-doped silicon bulk, and then applying a large reverse bias voltage between these implants and the backplane of the bulk. Position resolution is achieved by segmenting these implants either into strips or pixels, but we'll come back to that later. I first want to look a bit in the physics of this p-n junction and how this determines the operating parameters of our silicon detector and how it affects its performance. Now, n-doped silicon is created by introducing a small fraction of so-called donor atoms in the silicon lattice. These are atoms with 5 valence electrons, so for example phosphorus. These excess valence electrons are very loosely bound. They occupy energy levels just below the conduction band and can essentially move freely through the lattice. So electrons are called the majority charge carriers in n-doped silicon. P-doped silicon is created by introducing a small fraction of acceptor atoms in the silicon lattice. These are atoms with 3 valence electrons, so for example boron. This introduces energy levels just above the valence band, creating loosely bound holes, which again can essentially move freely through the lattice. So holes are the majority charge carriers in p-doped silicon. Now, if we bring a region of p-doped silicon into contact with a region of n-doped silicon, we get density gradients of majority charge carriers across the junction. On the p-doped side, we have an excess of loosely bound holes. On the n-doped side, we have an excess of loosely bound electrons. And as it always happens when we have a density gradient, we get diffusion of these majority charge carriers across the junction. Electrons that diffuse across the junction into the p-doped region will recombine there with acceptor atoms. Holes that diffuse across the junction into the n-doped region will recombine there with donor atoms. The result is the creation of a so-called depletion zone across the junction, which is depleted of free charge carriers. But the diffusion of these electrons and holes across the junction also represents a net movement of electric charge, and this causes the creation of an electric field across the junction. So the system finally will reach an equilibrium, a steady state in equilibrium between the diffusion that is driven by these density gradients and the Coulomb force created by the electric field. Now we can calculate the electric field inside the depletion zone and the intrinsic bias voltage that is created across the depletion zone if we integrate over the charge density in the depletion zone. And the charge density on either side of the junction within the depletion zone is of course given by the densities of acceptor and donor atoms on either side of the junction. Now if we do the integral and calculate the voltage drop, we find that the intrinsic bias voltage is given by the density of donor atoms on the n side of the junction times the thickness of the depletion zone on the n side of the junction squared, plus the density of acceptor atoms on the p side of the junction times the thickness of the depletion zone on the p side squared. Now the total charge of course has to be conserved. So if we integrate over the charge over the width of the depletion zone, this has to be 0, which means that Na times dP has to be equal to dN times Nd. Now remember that in our P and N detector we have thin p-doped implants and a thick n-doped bulk, and we want the depletion zone to extend into the n-type bulk. That means we want to have dN much larger than dP. And this of course we can achieve by making Na much larger than Nd. So by making the doping in the P implants much stronger than the doping in the n-type bulk. And if we do this, we can essentially, because dN is much larger than dP, we can neglect this term in the equation here, and we can calculate the thickness of the depletion zone in the bulk from this simple equation here. Now if we put in a typical value for the depletion, the doping concentration in the bulk, we can calculate that the intrinsic bias voltage of the junction is 0.65 volt, and the thickness of the depletion zone will be 25 micrometer. Now this is of course much smaller than the thickness of our bulk, which is typically 300 micrometer. But we can increase the thickness of this depletion zone by applying an external voltage here which has the same polarity as the intrinsic bias voltage. Now again, putting in typical numbers for the thickness of the detector and doping concentration, we can calculate what the so-called full depletion voltage, the voltage that is required to fully deplete a detector of thickness D. And what we find is that this is of the order of 100 volt if we put in these values here. So by creating a p-n junction between the implant and the detector bulk, we get a depletion zone and we get an electric field inside this depletion zone. But the intrinsic thickness of this depletion zone is small. So we apply an external bias voltage between the implant and the backplane of the detector in order to increase the thickness of the depletion zone. We speak of full depletion when the depletion zone extends all the way through the bulk to the backplane. But at the point of full depletion, the electric field at the backplane is 0. So we operate our detectors over depleted in order to increase the electric field everywhere in the detector, which leads to faster charge collection, so faster collection of the electrons and holes that are created by an ionizing particle going through our detector, and leads to a faster signal, and this is good for the rate capability of our detector. Note that in a P and N detector, so with P implants in N bulk, the electric field points towards the implants. So what we collect on the implants is actually the holes. Now the signals on the implants is induced by the drifting charge carriers. And the drift velocity of the charge carriers in silicon is directly proportional to the electric field. The proportionality constant between the electric field and the drift velocity is called the charge carrier mobility, and this is roughly a factor of 3 larger for electrons than it is for holes. For an over-depleted detector, the maximum drift time and therefore the duration of the signal is proportional to the square of the thickness of the detector and inversely proportional to the charge carrier mobility and the bias voltage that we apply. Now for our canonical thickness of 300 micrometer and assuming a bias voltage of 200 volt, remember we had estimated the full depletion voltage for our canonical detector to be of the order of 100 volts, so this would be significantly over depleted. We can calculate a maximum drift time for electrons of 3.5 nanoseconds and for holes of 11 nanoseconds. And remember that on a P and N detector we collect the holes, so this would be the duration of our signal. The evolution of the signal as a function of time is depicted here in this graph on the right. This is for slightly different parameters, so the time scale is not exactly the same. The signals are a little bit faster. But what you see is here in magenta the signal that is induced by the electrons on our P implant, and you see that the signal decreases with time as the electrons drift away from the implant towards the backplane, and then it breaks off as the electrons reach the backplane. The signal induced by the holes increases with time as the holes drift towards the implant, and then again it breaks off once the holes have reached the implant. Now, a very important parameter for the successful operation of a silicon detector is its so-called signal-to-noise performance. We have to apply a cut on the amplitudes of the signals that we measure in the detector in order to decide whether we think that a particular signal that we have measured was actually caused by an ionizing particle going through our detector, or whether it's just some random signal caused by noise in the detector or the readout electronics. Now the signal amplitudes from ionizing particles should of course follow a Landau distribution, whereas noise signals follow some random distribution that should be centered around 0. Note however that noise will also cause a broadening of the Landau distribution that we actually measure with the detector. Now in the picture shown here, the situation is pretty clear. The noise distribution and the distribution from ionizing particles are well separated from each other, and we can apply a cut in between the two distributions, essentially suppressing all the noise while keeping all the signal. But now imagine a situation where the noise is much larger and the two distributions overlap with each other. Now we have to make a compromise. Either we want to keep full efficiency of our detector, that means we have to apply a low cut, but that implies that we have to accept a lot of noise hits in our detector. Or we want to suppress the noise efficiently, then we have to apply a higher cut, but that means that we cut into the distribution for ionizing particles and we lose efficiency. The figure of merit that is used to measure the signal-to-noise performance is the ratio between the most probable signal for a MIP, so essentially the peak of the Landau distribution here, divided by the RMS of the noise distribution. These are two quantities that can easily be measured in a detector. As a rule of thumb, according to this definition, you need a signal-to-noise of at least 10 or better in order to have a functioning and efficient detector. Now note that the position of the Landau distribution, so S, is determined by the detector's thickness. So if we can make the noise N smaller, we can also afford to make the signal S smaller, and that means we can afford to make our detectors thinner, which is of course beneficial to reduce multiple scattering and energy loss of particles in our detector. So it's very important to understand the sources of noise. Now, one source of noise is statistical fluctuations in detector leakage currents. These detector leakage currents are essentially caused by thermal excitation of electron-hole pairs in the bulk of the silicon. And these can be suppressed very effectively by operating the detector at low temperatures. Another source of noise is current fluctuations in resistors, and in particular in the serial resistance in between the detector and the front-end amplifier. And in order to keep this noise small, it is important to keep this serial resistance as small as possible. And we'll come back to that in a few slides. Another very important source of noise is charge fluctuations at the input transistor of the preamplifier. And this noise is proportional to the capacitance of the detector that we connect to the amplifier. Now, and this dominates for short integration time. So we see in this plot here the different noise contributions as a function of the integration time of the amplifier. And at the LHC we are at something like 25 nanoseconds here, so in the range where charge fluctuations, which are proportional to the detector capacitance, dominate completely. So that means if we have a large detector capacitance, for example, we have long strips in our silicon strip detector, we get larger noise, and that means we have to make our detectors thicker. Conversely, if we can make our strips shorter, or we go to pixel detectors with small cell size and therefore small capacitance, we get less noise and we can afford to make our detectors thinner. Okay, let me conclude this part of the lecture by trying to illustrate very briefly what it takes to turn a detector concept in a real detector that works in an experiment. Now, this sketch here shows the basic elements of a simple P-N strip detector. You have here the P-type implants on top of the N-type bulk. And what you see on top of each of the implants, you have a metal strip here in order to minimize the resistance along the signal path towards the edge of the detector. At the end of this metal strip, close to the edge of the detector, you have a bond pad that allows to connect a wire bond to a readout amplifier. The metal strip is typically AC coupled to the implant through a thin insulating layer of silicon oxide here, and this is done in order to protect the readout amplifiers from DC leakage currents in the detector bulk. Now, a typical detector module consists of a silicon sensor and a readout hybrid that carries several front-end chips, connectors for signal, low voltage and bias voltage, and probably some capacitors and resistors for voltage filtering. Front-end chips typically include 128 input channels and integrate amplifiers, comparators or analog to digital converters, digital logic for data processing, for example for zero suppression, and formatting of the data, and then output line drivers to allow transmission of the signals via cables to the outside world. Now, a typical silicon sensor is 10 centimeters wide and 10 centimeters long. This is due to the size of the wafers from which these silicon sensors are produced, and a 10 centimeter wide sensor with a pitch of about 200 micrometer will have 512 strips. So a typical front-end hybrid will carry 4 front-end chips and not 3 as shown in this picture here. Now, in addition to the silicon sensor and the hybrid, you also usually need a pitch adapter in order to match the strip pitch of the silicon sensor to the input pitch of the front-end amplifier. And of course, you need some supports to hold all this together. Now, of course, it's again important to minimize the amount of dead material. So these supports, the pitch adapters, the readout hybrids, everything has to be as lightweight as possible. Pitch adapters usually use aluminum traces on a thin 200 micrometer thin glass or ceramic substrate. Readout hybrids are typically implemented using copper traces on a thin 80 micrometer thin polyimide feed, so film or Kapton. Supports, you see here the effort that is made to make the support as small as possible and usually uses light materials such as carbon fiber. And then of course the unavoidable connectors and cables to transport the signals and supply voltages to the outside world. And of course we need cooling for the electronics and the sensors. And these last points often dominate actually the material of the detector. Now if a sensor is 10 by 10 centimeters and you want to cover a large surface, you have to put many detector modules together. And this is another engineering challenge because you have to provide lightweight support structures for these many modules that on the one hand allow to position the modules to incredible precision of maybe the order of 100 micrometer over distances of several meters, that are stable over several years against vibrations, temperature, humidity variations, radiation damage, fire hazards, but at the same time of course should have as little material as possible again. And then of course there are the supports and the services, the cables and the cooling, which usually dominate the material of the detector. And again here also there are very interesting challenges for engineers to invent, for example, new powering schemes for the detectors in order to reduce the number of cables that are required. Okay, I've also mentioned that the implants can be segmented as strips but also as pixels. And segmenting the implants in pixel of course has many advantages. First of all, it provides much finer granularity, which allows to deal with higher particle density. Also, you measure two coordinates at the same time in one detector, and this makes it easier for track reconstruction algorithms. You have smaller cells because typical size of pixels is 100 by 150 micrometer, whereas the typical pitch of a strip detector, let's say 200 micrometer with 10 centimeter long strips. So you get much smaller capacitance in a pixel detector, which means less noise, and therefore you can make your detector thinner. The price you pay, of course, is the large number of readout channels. And as you remember, readout channels cost money. And just to give an illustration, the CMS pixel detector, which covers an area, active surface of just 1.24 square meters, has 124 million channels. Another complication of pixel detectors is that, of course, you need a separate readout amplifier for each of the pixels. And unlike strip detectors, you cannot position these readout amplifiers at the edge of the detector. You have to have a readout amplifier on top of each of the pixels. And the way this is usually realized in so-called hybrid pixel detectors is that you have two separate wafers of silicon. So there is one wafer that has the sensitive volume, so the pixel detector itself, and then there is a second wafer which has the front-end amplifiers. And the two are joined together by so-called bump bonding, where you have one of these little ball bumps in between each pixel on the detector and the corresponding connector on the readout chip. Okay, with this I'm at the end of this part of the lecture, and I leave you again with a very easy quiz which we will discuss with each other when we meet next week.